recording, and I'm going to share my screen. And I think I'm set back up again. Okay, and now I'm just going to spread you all out so I can see many of you at once. And we did lose a lot of time, but I dilly-dallied in the first class, so maybe we'll end up at the same place as before. So, sorry about that, but let's get started. Any questions before we get into it? And if not, that's good because we're way behind, and there'll be time for questions at the end if you can stick around. So let's play as much catch up as possible. Now, first of all, I've put up our pre-class warm-up question, and you can all see it, right? Nod your head if you see it. Okay, so go ahead and take just a moment to give that a go. Normally, I encourage you to show up maybe 10 minutes early and to take a crack at the warm-up question. And this one's pretty straightforward. This is just an exercise in unit conversion, though maybe with units that you're not super familiar with. Some of these will be much more interesting, some will be challenging, some will be brain teasers, and some of them are designed to point out common mistakes that people make. And then when the class does not perform well, and some of them are designed to catch you on those kinds of mistakes, I will throw you out, not throw you out, I'll throw you into breakout rooms, and you'll be forced to socialize with each other as your punishment for getting it wrong, and then we'll vote again. But today it's more to learn how to use this interface, the skynet.unc.edu SETI interface. And I believe there are 90 of you in the class, but who knows how many are left after our technical problem today. It appears most of you are still here, so that's good. Now I'll give you another 30 seconds to get an answer in there. Okay, and I'm going to make some other announcements. Feel free to keep working on this in the background. So some other announcements. A number of you are here probably for the first time. We, of course, had our first class on Monday. This is our second class. In the first class, we just went through the syllabus. I have that here. And you can find a copy of it on the Sakai site. And so if you weren't here last time, definitely go get a copy of the syllabus and read through it. And another announcement is the office hours. As I said, my office hours on Thursday from 2 to 3:30, and I'll just be available. You can drop in, but not this first week. This first week I have another appointment during that time, so I have to cancel the office hours this week. But that's not too bad because homework one's not due for a while, so not a big deal. And if you do have any pressing issues, you can certainly email me. Other announcements, I record the video, and I'm just going to stop sharing my screen for just an instant to make sure that I am recording this. And indeed I am, so good. I'm going to share the screen again. So I record the videos, I record the first class, the first section and the second section, and whichever one is better, I will post onto the YouTube site, also linked in the syllabus. And you can see that's this new list down here at the bottom. Right now it just has the one entry, our orientation.
Constellations.
Oops,
How
one
many
second.
of you took this course to learn the constellations?
It has a video that starts, so it has some audio there. And I'll break these out by lesson. And so you can find material a little bit more easily. You can go into a lesson, and that lesson will have probably a couple classes, and I'll try to provide some information about what was in that video in case you're going to look for it. And of course, I have older videos here that you can go to for information as well. Another announcement is the ebook. So once you get into WebAssign, which since my computer just crashed and I rebooted, I'll have to log in again. Which only take us, well, they put me right on the student page. That's nice. So this is the student view, and you have the ebook here, which has the reading assignment. It has math notes and of exercises, a variety of things. I've learned that those of you who have not yet paid for WebAssign don't have access to the ebook. And once you do pay or type in that access code that you've ordered from the bookstore, then you will have access to the ebook. So I know some of you are waiting to get that access code from the bookstore, and some of you haven't paid because you're planning on using that full 2-week grace period. And so the downside is you don't have access to the ebook. I'll say a couple things. In terms of the reading assignment, just read chapter 1 and you'll be fine. That will get us through the first week or so. But also what I'm going to do is, especially for those of you who have not gained your access code from the bookstore and can't get into WebAssign at all, what I will do is I will make a PDF of homework 1 and a PDF of the ebook notes for lesson 1, and I'll put those someplace where everybody can get to it. Either in the announcement area, but also just a general web link for those who can't get into WebAssign yet. So I think those are my general announcements. Hopefully that helps some of you. But questions, any questions about that before we get into the first stuff?
I got my WebAssign access code for the lab. Is that active? I tried putting it in last night.
It is not active for the lab yet. As I mentioned maybe in the last lecture, we did a major upgrade to the lab this summer, and the publisher just got that stuff back to me, and I found some things I didn't like, so I'm iterating with them. But it's not a problem because the labs are not meeting this week, and next week it's just a basic orientation. That buys me some time to get these kinks worked out with the publisher, just to minimize confusion for you all, and I will set those up as soon as they're ready and definitely before you need them. Since the labs are starting slowly, it's not that critical. That explains that for you. Any other burning questions? As I will madly try to catch up after my blue screen of death. Okay, the first thing I wanted to do was pitch the lab course a little bit. Let's see if the prompt cam came up. So the lab course, it's optional. You don't have to take it. But if you do take it, you satisfy your PX requirement. That's Science with Lab. And this is a cool way to do it. There's no astronomy lab out there like this. We developed this at UNC. It's now been adopted by a dozen institutions. And NSF has recommended a proposal that we wrote. They'll bring in another $2 million to expand it to 3 dozen institutions. So it's a growing national and international curriculum that makes use of our telescopes. As I think I mentioned last time, one of the things I do is I build telescopes all around the world, generally for science and cutting edge research, but I'm passionate about education. So I've reserved a little bit of time on each of these telescopes, some located at the best observatories on the planet, for you all to use, and for other educational programs that my Skynet array is involved in. Anyway, I'll tell you just a little bit about it, and then I'll tell you how the labs are going to work this semester in case you want to get in. And this is a live webcam of our primary site in the foothills of the Chilean Andes. The US government has an observatory down in the southern hemisphere, and we've gained some space at the observatory where I've built 8 enclosures, the 6 little ones you see here, and then these 2 big ones. And these are robotic telescopes. They're fully automated. There's no human that works in these domes every night. They're under computer control. And with some of the money NSF has given us, we've made an interface that works as well for professionals as it does for students. Going all the way down to the middle school level, they use this interface, which means you all will be able to use it too. And that gains you access to professional quality telescopes, the best sites in the world that are used right alongside you. Professionals will be using them, making cutting edge discoveries. So that's kind of a cool opportunity. We built these telescopes. Maybe I'll pull up a little video here. Oh, it's hiding somewhere. One second. There we go. Let me adjust you all on my other monitor, shrink you over a little bit. This should start. So this is, we began doing this in 2004. This is how to build 6 telescopes in 60 seconds. We had a camera on it that took a picture every 10 minutes, and we weeded out the nighttime and the bad weather and stuff like that. Again, initially funded by the National Science Foundation. These were originally built to explore cosmic explosions called gamma ray bursts. That's my personal area of research. These are massive stars, 20 to 30 times the mass of our sun, that have come to the end of their life and formed a black hole. And as they die, they produce a burst of gamma rays. And orbiting around the Earth, NASA has a collection of spacecraft that monitors the skies in gamma rays. If they find one of these bursts, they radio the coordinates down to us within tens of seconds. And our telescopes reposition themselves to observe these cosmic explosions. That's what they were built for originally. Now they do everything imaginable with small telescopes, a wide variety of science, discovering new objects out beyond Neptune and asteroids and supernovae and distant galaxies and variable stars, and the list goes on and on. I've also built, maybe I'll flip to another video, I've built these telescopes around the world. That's our original site and our best site, but we've built telescopes in Australia and in Canada, and there are many telescopes across the US that I did not build that have joined our network, and as students you will have access to all of them. And this is a movie just showing how automated it is. At the beginning of every night, when the sun drops a degree below the horizon, the telescopes open automatically and slew into position. You see one person walking around back there. That's not one of ours. He's working on one of the other telescopes there. And as soon as it gets dark enough, they start carrying out the observations. It's a queue-scheduled system, so if you join the lab, there's a web interface, and we show you how to use it and put in your requests. And you don't have to stay up all night. You can go to sleep, and Skynet, which is the name of the system, the computer brains of the system, it is a movie reference, will carry out the observations and get the data back to you. I'll show you just a couple more items. Yeah, so here's a picture of me standing next to one of the original telescopes, to give you a sense of scale and also to make it look even cooler than it is. These are 16-inch diameter telescopes. That's the size of the mirror. And maybe I'll make this bigger. And we've since been upgrading them to larger telescopes. This is a 24-inch telescope, and then we take the smaller ones and deploy them around the world. So if one site's weathered out, you can still observe from another site. Here's another picture of the observatory at night, and this is what it's like to be there. The sky actually looks like that, looking up to the human eye. It's just amazing to work at some of these best sites. That bright star near the bottom is actually the planet Venus. And here's a zoom out of the observatory in the foothills of the Chilean Andes. And these little telescopes right here, these are our Skynet telescopes. They're called Prompt. But there are other telescopes that belong to other institutions, and it's a 2-mountain observatory, and on the second mountain, UNC has its signature 4-meter diameter telescope. Again, that's the size of the mirror, a rather large telescope. In this lab, you'll just be using the smaller robotic telescopes, not just here, but all around the world. And one last picture, this was taken in winter, and those are cloud tops. Often when we're there working, this is winter, which is summer up here in the northern hemisphere. We're working above the clouds, so it's a cool experience. And I, of course, can't take you all there, but if you do decide to take this lab, you'll have access to these facilities, which is kind of cool. And also, in addition to the optical telescopes, we've integrated a radio telescope. This is in West Virginia. Observes the invisible universe. You can use it day and night. And this is 6 stories, excuse me, 6 stories tall and 150 tons. And in the lab, you'll be moving it around to measure things about the galaxy. In this lab, you actually weigh the galaxy using this telescope. The labs start off just by learning how to use the system, taking pictures of all sorts of things. But as you go on, they become more scientific, and you reproduce the great discoveries of the past 400 years. And although Astro 101 only deals with the solar system, this lab course includes the whole universe. So Astro 101 and 102 material to give you an experience there. Some other things about the lab. It's the way we're working it this year because of COVID is we do have scheduled time slots. They've been pushed back. They're normally earlier in the day, but given how UNC has rescheduled things to accommodate transitions between classes for COVID, these are occurring in the early evening, and those will be done by Zoom. And so you'll soon be receiving information from your TA, a grad student that I will train, and I'll pop in on some of them as well. And the TA will start by giving you a general orientation to that particular lab, but then the rest of the time you can stay or go. And you don't have to do the lab at that time. You'll be able to do it on your own, at your own pace, as long as everything's done by the due date. We're going to use those scheduled times more for a quick presentation and office hours. And we've set up discussion boards on Sakai. They're now, as of last night, they're Sakai sites for the labs. And where you can introduce yourself, and then for each lab, the students will post and interact and ask questions and answer questions, and they could be questions not related to the lab, should be related to astronomy. But in my experience teaching this class, this lab, both in person and online, you actually get more interaction with the other students and with the instructor over these discussion forums. So it's not a bad way to go. So most of the teaching and instruction will take place there. The instructor will check in every day to answer questions. And again, the scheduled time will be more for office hours. Trying to think if that covers everything. It's listed in Connect Carolina as hybrid, and really we're offering it in a completely remote format. There will be a couple activities that we do on campus, socially distanced, outside mostly, but there will be equivalent activities that you can do remotely for the same number of points. So you can take it in either form. Now I'll just pause there and ask if there are any questions about the lab course.
For textbooks, do you have to buy that $78 Skynet access code from the student stores?
It does have a separate web assign. It's pricier than the one for this course, though it is essentially a full textbook. It's online and interactive, but it's like a 100-page textbook. You're not going to do traditional lab reports. You'll read through the material. There's a bunch of videos that I've recorded that are linked into it, and you go through it, do the activities, and then answer the questions as you go. And that's why WebAssign charges more for it. It's pretty involved. In fact, I think it's the most advanced thing they've ever put together and offer. You know, they're a separate private company, so they charge more for it. But what I give you is the telescope time for free. I give each student 30 minutes of telescope time, which we do sell telescope time. That's how I keep my research group alive sometimes. You're getting essentially $40 worth of telescope time for free as part of the $65 cost. If you buy it through the bookstore, they mark it up even more. If you buy it directly, it's $65. So that's the deal there. And again, I can't remember if I said this, you can take it this semester, you can take it a later semester. If you are trying to get in, there are still sections with space. Normally they fill up, and then I slowly raise the caps. So don't give up. You can keep trying to get in, and we'll get everyone in who wants it this semester. And again, there are no labs this week. and you'll get your first lab is next week over Zoom, and it's just basic introduction, orientation, syllabus stuff. Then lab 1 begins in earnest the week after that. Other questions? Okay, so let's check out our warm-up question. So I think I have it here. I think I have 2 instances of this going. Let me kill that one. Okay, so again, this is a pretty introductory one. There's nothing very sexy about this question. It's just practicing unit conversion and getting used to different units. Let's see what you all came up with. I got 39 responses. I think I have more than 39 of you present. So I'm going to give you another 15 seconds or so, 15, 20 seconds to give it a go and submit your answer. Those of you who, I'm not using this to take attendance. I'm not capturing your name or who you are, so there's no risk of embarrassment. It's anonymous. But those of you who do it, usually do better on the homeworks and exams. This is an opportunity to get some practice. So I'll hush for the next 30 seconds. Can we get it up to 50? There's 46. I'd settle for 47. There we go. Okay, 47. So let's see how you answered. Show your values. And I see a lot of the correct answer. Put in this histogram mode, maybe add a few bins or something. But yeah, most of you got the correct answer, 900. I'm going to work it out real quick on the dot cam and show you how I recommend that you do unit conversion. So let me scooch over here just a little bit. So with unit conversion, you always start with what you know. And I gave you 1/4 of a degree, and I'm asking you to convert it into arc seconds, which is a unit, an angular unit of measure astronomers use a lot. So I strongly recommend that you use the bracket notation. You see it in chemistry class a lot, and it's great for not mixing up the units or getting it backwards. For example, we're starting in degrees. We're going to go from degrees to arc minutes. 1 dash is the symbol for arc minute. And then we're going to go from arc minutes into arc seconds. And if you put your units in here, you won't get your numbers backwards. For example, in 1 degree, we know there are how many arc minutes? Anyone want to shout it out?
60.
60. So if you have your degrees, your units in there, you're going to get it in the right place. You know the conversion's 60, but do you multiply? Do you divide? Sometimes people get confused there. But if you mark your units here, the degrees will have to cancel. So it will need to be on the bottom. The 60 will end up on the top. Same deal. 1 arc minute is 60 arc seconds. And so the arc minutes cancel, so the answer will be in arc seconds. And then you multiply each thing in the top and divide by each in the bottom. And you do that, and you get 900 arc seconds. That gives you an example of unit conversion. This is a pretty straightforward example, and most of the math I do today is going to be really straightforward, basic stuff, just to get us started, to get us all on the same page. Okay, with that done, let us move on to the first topic, which is going to be size and scale in the universe. The universe is just incredibly big. I can't convey how big it is. It's hard for me as a professional astronomer to wrap my mind around how big and vast the universe is. And so even the professionals, we have to rely on tricks for thinking about the sizes and scales of things. Like we know facts as well. Like a galaxy cluster, a cluster of galaxies is typically a megaparsec across, and that's just a fact. And it probably doesn't mean anything to any of you, Even if you knew what a parsec is, 1,000,000 parsecs, you don't have in your mind some way to relate to that vast kind of distance. But if you know that, well, galaxy clusters are full of galaxies, how much bigger is a galaxy cluster than a galaxy? That might be a relatable number. How much bigger is a galaxy than a stellar neighborhood? How much bigger is a stellar neighborhood than a solar system? How much bigger is a solar system than a star or a planet? So if we do this in little jumps with numbers that we understand intuitively, then that's how we can think about the vastness of the universe. So I think that's where we're going to start. Oh, and here's just a slide showing the difference between a degree, which is 1/360th of a circle, 60 arc minutes in a degree, 60 arc seconds in an arc minute. But anyway, in terms of scale, let's start with the Earth. Because this is an object that we have some comprehension for. And I'll just announce now, I'll probably go just a couple minutes over, given the technical difficulty at the beginning. If you have to leave for another class, not a problem. I just want to get it recorded on the video. You can come back and watch the end during the video. So just so you don't feel I'm being rude by going over, that's my spur of the moment plan. I will go over, but you don't have to stick around. You can catch it later. Okay, so the Earth. This is an object that we all have a good intuitive feel for, a sense for. How many of you have flown from one continent to another? Yeah, a good number of you. And so you're in a plane, you're in the plane for a certain amount of time. You have a feeling for how fast planes fly because you've seen them flying across the sky. That gives you a feel for that distance you covered. And if you went from one continent to another, then you covered a fair fraction of the Earth, and you hence have a sense for how big our planet is. Even if you never did that, how many of you have done a road trip across the country from one side to the other? Yeah, a good number of you. I've done it a number of times, and it takes a couple of days depending on how much driving you do. But again, you have a feel for how fast cars travel, you know how long you were in the car, so you get a feel for the size of our country. And as you can tell from this picture, our country is a certain fraction of the size of the world, so multiply by a factor of a few, and that's how big the planet is. So even if you haven't done that, there's this thing you can try. There's a program called Google Earth. It's like Google Maps, but it's a little bit better. And I have a link to it in the ebook. Download it. It's free. And zoom into something you know, like your house, and tell it to take you to the other side of the country. And it'll put you on a little suborbital hop. And as you zoom out, you'll see your house, your neighborhood, your city, your state, the country, and then the same stuff as you zoom back in. And after you do a number of these hops, you'll get a feel for how big the planet is compared to things you understand better, like cities and states. Okay, so all of you have some sense for this object. So let's move up in scale. What is this object? It's all easy questions today. What's this object?
Sun.
Yeah.
Sun.
Questions will get more challenging and interesting, I promise. But we'll take it real easy today. So yeah, this is the sun. Now, if I go back here, it says the Earth is 15,000 kilometers across. The sun is 1.5 million kilometers across. So the sun is how many times bigger than the Earth?
10.
Not 10.
1,000.
Not 1,000.
100.
100. It's 100. Now there are 2 extra zeros in this one than the previous. So our sun is 100 times bigger. Let's get a feel for that. I'm going to put the cursor in the middle here. That's half, a quarter, an eighth, a 16th, 32nd, 64th, 1/28th, maybe somewhere around there. Between the edge of the sun and the left-hand side of my cursor is 1/100th the sun. That's the diameter of the Earth. So the Earth is tiny compared to the sun. It's about the size of one of these spots, one of the smaller ones. What are these called? Sunspots. Yeah. Again, easy questions today. Those sunspots, they're regions of magnetic activity. The magnetic fields are impeding the flow of energy from underneath. So they're a little bit cooler, a little bit darker than the rest of the surface. And we talk, Astro 102 begins with our sun. Anyway, okay, so that's how much bigger the sun is. And I should say, stars vary in size. Some stars are 1,000 times bigger than our sun, and some are much smaller. There's some stars the size of our planet, dead stars called white dwarfs. Some dead stars called neutron stars the size of Chapel Hill, a city. And some, like black holes, can be infinitely small depending on how you measure them. So stars range in size tremendously. Let's jump up to a much bigger scale. Probably skipped a couple rungs here. This is a galaxy. Is this our galaxy?
No,
No.
Andromeda?
maybe.
I don't think it's Andromeda. It's not our galaxy, but why can it not be our galaxy?
We can't get that far out yet.
Exactly. We can't get that far away yet. The farthest we've ever traveled is with the Voyager probes, just to the outskirts of our solar system. And that's smaller than a pixel in this image. And so this is some other galaxy. It's a galaxy that's about the same size as ours, spiral like ours, but it's not ours. If you ever see those t-shirts with the galaxy and an arrow saying, "We are here"? No, we aren't, because we've never gotten a picture of our galaxy from the outside. We can't get far enough out to do it. It's usually a picture of Andromeda, and they've said we are here incorrectly. Anyway, galaxies are really, really big. A galaxy like our own has 100 billion or a few 100 billion stars in it. And we have to introduce a new unit of measure, because if we're sticking with kilometers, this is 1,000 quadrillion kilometers across. That's a quintillion. And I know none of you have an intuitive feel for a quintillion of anything. I don't anyway. So the way we deal with this is we introduce this new unit called a light year. And what's the definition of a light year? Anyone?
The distance light can travel in 1 year.
Right. How far light travels in a single year. So let's write some of this down. I think I'll go to a fresh page here, bring up the doc cam. Where the hell is it? There it is. Okay. Okay, so light year. And I'm going to take this slowly and do a few calculations here, just to give you a little bit of practice, a little bit of experience. As I said, 1/3 the course is computation, but I want to start slowly to bring everyone along. So you said the distance light travels in a year. Well, that's an equation. That's our first equation. And the equation is distance is equal to speed times time. It's probably the most straightforward of the equations we'll cover in this course. It's one that you all have an intuitive feel for. Whenever you travel some distance in the car, you're making use of this equation in one way or another. How far do I have to go? How much longer do I have to go? And actually, before we talk about light year, let's just use this equation, an example of using this equation to demonstrate some of the math skills that you'll need in this course. So I'll just do a little aside here. First, let's write it in symbol form. D for distance, V for velocity, speed, times time. So there's our equation. And suppose I gave you an example. Suppose we travel 100 miles in 2 hours. Nope, I did that. No, that's right. Yeah, suppose we do 100 miles in 2 hours. How fast do we go on average? Let's say that's the question. So the first thing you're going to need is to solve this equation for V, the speed, and you do that by what? How do you solve this equation for speed?
Divide both sides by time.
Divide both sides by time. Again, this is the simplest equation. It will get trickier, but it's all just high school algebra 1. Divide both by time. T cancels out, so you've isolated the variable of interest. This is what I gave you, and this is what you want. Then the next step is plug and chug. So we're going to plug in, I said 100 miles, and what did I say, 1 hour or 2 hours?
2 hours.
2 hours. Plug in 2 hours. So you can plug that in a calculator, do it in your head. That's 50 miles per hour. Just an example of the kinds of math we'll need to do. In fact, I have a sheet here summarizing the math that's required in this course. If I give you a question, first you have to find the right equation. What have I given you? What am I asking for? What equation has those variables? Now the nice thing is the math notes, the ebook, it's all in the order I teach the material, as are the homeworks, as are the exams. So you open up that ebook and you have your equations in order, that's probably the order you need to use them, so that will help you figure out what equation to use. Solve for the variable of interest. In this case, it was velocity, speed, which is again just high school algebra 1. Plug and chug, enter the numbers, maybe into a calculator, get the answer. Then you do a sanity check. Suppose I gave you a problem and you're calculating the distance to Jupiter, and it came back as 1 meter. Jupiter is not 1 meter away. I'm reaching 1 meter away and there's no Jupiter there. Look at your answer. Don't just submit it blindly. Say, could that possibly be? If it can't, you made a mistake. And then often there will be a unit conversion. And we've already done an example of that. You may get the answer in one form, but you need it in another. Okay, and it's technically past the closing time. So if you have to go, I understand, but I'm gonna finish the size and scale part just for the video. Okay, back to light year. So let's use this equation. 1 light year, Ly, is the distance light travels in a year. Light travels at the speed of light, which is c. C is our symbol for the speed of light. And what is the numerical value? Does anyone know the speed of light? Let's say in kilometers per second.
300,000.
300,000, exactly. 300,000 kilometers per second. And often we'll use scientific notation. So in scientific notation, that's 3 times 10 to the, what
6.
number? Not 6, close.
Fifth.
Yep. And just for those of you who haven't done this for a while, you take the decimal point, you move it 1, 2, 3, 4, 5 spots. That's how you know. Now, sometimes we may need it in meters per second. And that would be 3 times 10 to the what meters per second?
7.
Not 7.
8.
8.
Meters per second. Again, I'll just demonstrate that as a bracket unit conversion on the side. You start with what you know, kilometers per second, put in the brackets. We know in 1 kilometer, there are 1,000 meters. So the kilometers cancel. It's gonna be this times 1,000. 1,000 is really 10 to the 3. So 3 times 10 to the 5 times 10 to the 8 divided by 1. You get 3 times 10 to the 8 meters per second. Okay, so we have the speed of light, we need the time. The time is 1 year. How far does light travel in 1 year? But what unit do we need that in? Okay, we got the speed in kilometers per second. Second, yeah. So let's do one more. I'll do it down here at the bottom. 1 year, again, I'm going to use the bracket notation. In 1 year, we have 365 days. In 1 day, and you know all this, we have 24 hours. In 1 hour, we have 60 minutes. And in 1 minute, we have 60 seconds. Cross off the numerators and denominators to make sure you had everything in the right order, top, bottom. Multiply these across the top and divide by each of these, which are just ones. If you put it into a calculator, you get approximately pi times 10 to the 7 seconds. It's not exactly pi, but it's a nice, easy way to remember it. And next time you're at a party and you want to impress your friends, no, don't do that. That's probably, that probably won't work. But anyway, that's the number of seconds in a year. This is the speed of light. So if we're going to calculate 1 light year distance is speed 3 times 10 to the 5 kilometers per second times the time of flight, pi times 10 to the 7 seconds. Seconds cancel, so the answer would be in kilometers. 3 times pi is what to an astronomer? Now I'll give you a hint. It's the same as 3 times 3.
9, approximately 9.
To an
Isn't it 10?
astronomer, 3 times 3 is
10.
10. So let me explain why that is. Distance is so hard to measure. Many things in astronomy are so hard to measure. It's not like the objects we're studying are right in our laboratory and we can measure things precisely. So often we round off. 3 times 3, 3 times pi, we just call it 10. Some things you have to be careful about, but something like this, we'll just round off. So this is 10 times 10 to the 5 times 10 to the 7. You add the exponents. The 10 times 10 to the 12 is 10 to the 13 kilometers. So that's how many kilometers are in a light year. And that alone doesn't help out your intuition, but you've gotten a lot of examples here of how to do calculations. Now, to help your intuition, let's consider the closest star. The closest star to us, other than the sun, is Alpha Centauri. It's a triple system. It's 3 stars together. The big one's called Alpha. And it is 4.3 light years away. And so that's the typical distance between stars, a few light years. So if you want to know what a light year is, it's the typical distance between stars in our part of the galaxy. So if we go back to this galaxy, it's 100,000 light years across. If I divide it by 4, then it means I'd encounter about 20,000 stars if I flew from one side to the other. Of course, there are hundreds of billions of stars because they're to the left and to the right and above and below, but on a straight line, you'd encounter maybe about 20,000. So that should give you a sense of scale of galaxies compared to the distance between stars. Just 1 or 2 more here. Let's jump up 1 more level. So before we're talking 100,000 light years, let's do it in light years now because that's more manageable than quintillions of kilometers. Going from 100,000 to 1 million. This is a factor of 10 bigger, and this is a group of galaxies. Galaxies group gravitationally. The nifty thing is the groups are just a little bit bigger than the galaxies themselves, a factor of 10. So galaxies can run into each other. In fact, that's how you make big galaxies. The little ones, we started with little ones in the universe. They merged over and over again to make big galaxies like our own. And some galaxies can be way, way bigger than even our own. And some can be much, much smaller. We call those giant galaxies and dwarf galaxies. We have a couple small baby galaxies, dwarf galaxies, orbiting our own. Here's another way. Oh, go ahead. Question.
I met a researcher at Elon who was researching dwarf galaxies, and he said that the black hole isn't always in the center because of the stars around it. Is that true?
Yeah, most galaxies have a big black hole at the center, and lots of little ones scattered throughout. In dwarf galaxies, they tend to be more messy, more of a train wreck. They sometimes don't have a super well-defined center. So they may not have a supermassive black hole at the center. But in a well-organized galaxy like our own, once you form one, it feeds, it gobbles up other stars and clouds of gas and can grow to millions or even billions times the mass of our sun. And so I think this will be my last slide of the day. So let me just put it up there. Same deal, start small, get big, but different transitions. This one starts down with humans, a scale we certainly understand, and they're floating next to the Hubble Space Telescope, which is about the size of the Space Shuttle cargo bay, because that's how it got up there, maybe a big bus or a small tractor trailer. Then their first hop is pretty non-intuitive. A factor of 500,000 gets you up to the size of the planet. Earth is 100 or 500,000 times bigger than Hubble. That's not very intuitive. Now, the next one is the solar system. It's 1,000,000 times bigger than our planet. And remember, the sun is 100 times bigger. And so if the solar system, all the orbits out to Neptune and Pluto, 1,000,000 times bigger, it means the solar system is mostly empty space. It's not like in Empire Strikes Back where you're flying through the asteroid belt, dodging things. If we send a probe through the asteroid belt, we may never see an asteroid unless you specifically design the path to go close to one. Another factor of 10,000 gets you up to our neighborhood of stars. And then it's about 15,000 neighborhoods from one side of the galaxy to the other. Again, many more neighborhoods. Just if you went in a row, there'd be about 15,000. Another factor of 10 to 20 gets you up to the local groups of galaxies. And another factor of 200, 300 gets you up to the largest scale structure. And one thing I forgot to mention that's kind of interesting, I said galaxies can collide. Stars barely ever collide. Stars are really small compared to the distance between them. Even if two galaxies run into each other, the stars usually don't hit. So galaxies can merge. Stellar mergers can occur, but it's much rarer. Anyway, I don't know if I hit everything I wanted to. I was rushing since we had the technical problems at the beginning. But the goal here was to give you a sense of how to navigate the vastness of the universe. Soon you'll, and particularly, for solar system, it's not as important because we're not going to go that far out. But in the lab course in 102, as we go all the way out, you'll need these tricks to try to get a feel for the largest scales imaginable. Okay, I think I'll stop there. Thank you for waiting the extra time, and I'll answer any questions until there are no more.
Thank you.
Thanks.
Thank you.
Thank you.
Thank you.
Thank you.
All right, any questions?
Hi, so are we reading the first chapter off of the physical textbook, or is it off of your the ones on the website, on WebAssign?
1 second, I'll stop the screen share. Okay, so I'm sorry. Ask the question again.
Okay, so are we reading the first chapter off of the physical textbook, or is it off the WebAssign
Right.
one?
You read it off the physical textbook. WebAssign, the thing in WebAssign, they call it an ebook, but it's not really a book. It's a collection of hopefully useful notes that I've put together for you. It gives you the reading assignment in the regular book. It gives you the equations, some worked out examples, some exercises. It's not really a book, though.
All right, thank you.
Sure. Other questions?
Is there anything that we're supposed to have? Because I know our quiz on the first chapter is in a couple of weeks. So should we just pace ourselves with reading that?
Yeah, just stay ahead of me in the lecture.
Okay.
I normally cover 2 or 3 of those subsections at a time. I only got through 1 today because of my technical problem. But if you stay ahead, you'll be fine. I also suggest opening up the homework ahead of time. As I'm talking about this stuff, if you've at least skimmed the questions, you'll say, oh, I see how to answer that. And you can maybe even answer it in real time if you wanted to.
Okay, perfect. And also, out of curiosity, what made you choose Skynet?
Let's see. We were down in Chile building the site for the first time. We got everything working. And none of us are instrumentalists, or at least I wasn't back then. So it's just by some miracle we got it all working. It was me, a couple undergrads. We were full of ourselves. We went down to La Serena, beautiful beach coastal town, having good food and drinks, and it just popped into one of my undergrads' heads. It should be Skynet, which, for those who don't get the reference, that's the computer program that became self-aware and took over the world in the Terminator series. And actually, we have another piece of software called the Terminator that works at each scope. Skynet talks to Terminators that controls the telescopes. So it hasn't become self-aware yet. If it does,
Okay, hopefully that's not bad juju, but
yeah, if it does, as its creator, I might be okay, but the rest of you are screwed. So
that's comforting.
yeah,
But thank you, Dr. Reichert.
my pleasure.
So how did you meet Buzz Aldrin?
So when I was an undergrad at Penn State, in my last 2 years there, I got a scholarship. Back then it was called the Mercury 7 Scholarship, and it later became the Astronaut Scholarship. Back then it was quite small. It's grown into like a full ride thing these days. I wish it was that back then. But it's organized by the astronauts, Mercury, Gemini, Apollo, and the Space Shuttle program, and then probably whatever we happen to have next, SpaceX rides and things like that. And as one of the perks, in addition to them paying some of your tuition and room and board, once a year you can go down and hang out with them. I've only done it twice. They are heroes, though I don't like hero worship. So, you know, but I did go down and hung out with them. It was really cool. We went to their favorite restaurant, ate food, got drunk together. Probably something I shouldn't have in a video I'm going to post online. And anyway, but you know, a lot of them have passed away since, but I got to meet many of the younger ones. In fact, my son, who's going to UNC Wilmington on Sunday for college, starting college, he was just a toddler the first time I did this. And we were in the hotel lobby, and he decided to make a run for the door. He liked doing that back then. And he stepped on both Buzz Aldrin and John Glenn's feet at the same time. So he has stepped on a foot that stepped on the moon.
Well, good story. Thank you. You have a good one.
Sure, my pleasure.
Yeah, thank you.
Anything else?
If you're gonna email a professor because you want to do like research work or like any work like that, trying to get in there, what exactly should you say? Just like, hey, I want to do work for you.
Yeah, it's always weird, right? I mean, the olden days would just knock on doors, which was maybe more effective. It's harder for them to put you off if you're physically there. But it's tough. Often professors will say no initially, and you have to be persistent. Or they may say, I'm kind of full up at the moment, but maybe later, then definitely follow up later. Since it's going to be by email, you know, ask if they have some time you can meet, maybe in office hours you can drop in and introduce yourself, explain your interests, that you really want to get into research early on. If you have some skill sets like programming, you could talk about that or other prior similar experiences. And it's a good way to start. At least you get a conversation going and you can cycle back around. It may take a year before you land such a position. And you know, working for credit, you have to fill those forms out like in the first week of class. So it's probably not going to work out for credit the first semester, but you can work for free, no money, no credit, if they'll just let you in. And then next semester you can work for credit, and then maybe over the summer for money.
Do any programs at the school like hold any extra weight as well? Because I know I'm in the accelerated research program, but I don't know if that like holds anything beyond like the resources we get out of that anyway.
I actually don't know anything about that program. So what do? Do they help make these connections for you?
I think it's partially that. I know a lot of it is you just get undergraduate research mentors, and I think we might have a better shot at getting research maybe, but I still have to figure that out.
Definitely go through that course as well, and it sounds like they'll be positioned to give you some advice other than what you're hearing from me now as well.
Thank you.
And the best way is if you can get summer money, and then of course they're going to work for you if you're already paid for. So, and there are opportunities. North Carolina Space Grant, and within the UNC system, there's something called SURF, Summer Undergraduate Research Fellowship. Those are 2 to target, but it helps if you've already spoken to a professor. Like one approach, if you're having a hard time getting in, is you could talk to a professor and say, hey, I'm applying for these, and I'd like to tailor them to your research group. That's always kind of flattering to them, and so they're more likely to meet with you and give you some information you can use.
Thank you. Oh, also, is there anything else interesting other than just exoplanets going on in the research here?
Yeah. So our last couple hires have been in exoplanets. We've been fleshing out that group, that subject area. In the past, we always hired each person in a completely different area. But we have 2 people doing exoplanets. They're both actually also instrumentation. One is planning to launch a network of satellites in time, and the other is building something called Everyscope, which is just an awesome experiment. It's a bunch of little telescopes combining into one that monitors the whole sky simultaneously. They're building a bigger version of that. We have people who work in Galaxies. We have 2 people who work in Galaxies and galaxy evolution. We have someone who works in variable stars, variable white dwarfs in particular, trying to study those objects by how they shake and pulsate. I do a variety of things, cosmic explosions. Recently, I've been involved in gravitational wave follow-up. That's something Einstein predicted, that certain kinds of events can send ripples out through space and time. And we now actually, we being like at the national level, have the ability to detect these ripples in space and time. Then they rely on people like me to search the sky trying to find an optical counterpart. It's only happened once, and we did it in 2017, and we were among the groups that did it. And we're about to get another $500,000 from NSF to tackle that big time. I know I'm skipping people. We have, then you have your more theory types, and they normally work with older students who have taken some courses and can be more useful to them theoretically. But we have someone who builds star forming regions on the computer, numerical simulations, dark matter, infall, and stuff like that. And we have someone who does theoretical cosmology, someone who does theoretical general relativity. So we have a nice sized group. We're not big enough to be our own department, but we have a lot of active researchers, and we have if you're interested in observation, this is an amazing place because we have the observational resources of a large astronomy department, yet it's a smaller number of faculty, which means we all have tons of telescope time, so much so that our students have tons of telescope time. You know, if you get into it early, you could be doing observations with our 4-meter telescope in Chile by the time you graduate. Whereas if you're at a place like Caltech, which I'm not putting down, I did my postdoc there, I love the place. Even the postdocs have to fight for time on a 4-meter telescope, you know. So, because they have like 50 faculty, something like that. There are unique opportunities here, and particularly on the observational side.
How competitive is that program that you said you do like right before school starts? Because
Yeah,
you said you
the
only take
Ryder
like what, like 15?
I take 18 students. It's a national pool, but half of them I take from UNC, Chapel Hill typically. And it's usually 2 or 3 times oversubscribed. So, you know, if it's, what do I, normally maybe there are 50 some applicants and I take 18, something like that. And the hint is I'm looking not for background. In fact, if someone applies with a background in radio astronomy, I don't take them because let's give someone else a chance. What I'm looking for is over-the-top enthusiasm. I try to find a collection of 18 people who just would love to have this experience, to be embedded in a real observatory for a week, thrown on the telescope on day 1, running it themselves, staying up day and night doing science and astronomy. There are, of course, many people that would be their worst nightmare, but I'm looking for the people who just drool at that opportunity. And I bring in astronomy educators from across the country. We have usually like 1 educator for every 2 students. It's an amazing ratio. And they're not getting paid. We do this on a volunteer basis just out of love of doing it. And so what makes it fun for us is having those kinds of students who are choosing not to sleep because they don't want to miss a single thing. And it's an amazing week for us as educators and for this kind of student. And if you express that in the short essay in the application, that helps your odds a lot.
Sounds good.
The other thing is we're looking for, I will take non-majors as well, but mostly we take majors between the 1st and 2nd year, kind of when they're making their decision. This is a help seal the deal experience. Sometimes I feel bad. It's so much fun that you'll never actually have this much fun in astronomy again, so it's a little misleading.
Would you recommend still applying for it, even if you are probably going to major in the space sciences anyway?
If you're not, or if you are?
If you are, sort of like just like applying knowing that you might be taking it away from somebody who might need that experience.
No. If you've already decided, I try to get as many of our astro majors through the program as possible. We used to only have like 5 per year. And things I've done, and others, and I can't take all credit, of course, we've brought in a lot of young, new, exciting faculty working at the cutting edge and instrument builders at the cutting edge. But things I've done like the lab course and splitting the intro astronomy course into 2. I've been able to generate a lot of, I've got a lot more people coming into the intro program, and consequently because of that, I've got a lot more people going into the Arriver program, and they come back as majors. So I think now we have 20 to 30 astro track majors per year. So it's grown tremendously, and I try to get as many of them as I can through it.
20 in total, like out of all undergrads, like 20 or 30 astro, like physics majors?
Out of all no, that's just the astro. So in the physics department, you have 2 tracks. You have physics and you have astronomy. We're doing 20 or 30 astronomers in the physics and astronomy department. And probably twice as many physics-only students as well. The numbers are somewhere around there.
Does it go like major in astronomy, or is it like you have like your physics majors and then you have the ones on the astrophysics track?
There are 2 tracks for the BS. For the BA, we have many, many tracks. We have like environmental physics, we have fiscal physics. There's a large overlap there actually. In other things, but on the BS track, which if you want to go to grad school, you want to do a BS, we have standard physics and we have astronomy. And basically it means all the electives in the standard, you'll be taking astronomy courses. So they all get the same degree. Physics and astronomy is what's on the degree.
Oh, also, are you doing that the Greenbelt radio? Is that where it is? The Greenbelt?
Green Bank.
Oh, Green Bank, sorry.
Yeah.
Are you going to be doing that again this year or next year? And also, like, when would the application be for that?
Yes, so the application's available now. It still has this year's dates, which was canceled, of course. But you can put the application in at any time, and I save all of them. And in the spring, probably around February, I'll email everyone, all former students, reminding them of the competition, of the possibility. And I think it's due mid-April, and we let you know early May. And it takes place beginning of August, typically.
All right, thank you.
Sure.
Yeah, thank you.
My pleasure. All right, if there's nothing else, I'll close this out.